Let us look once again at type B and type A uncertainties. How to use them, when to use statistical calculations, confidence intervals, and when to use tolerances of our burettes, pipettes, balances, spectrophotometers, and other devices. Let's look at one example, procedure for determination of manganese in tea leaves. Surprisingly, tea leaves contain quite a lot of manganese metal. Most of other plants do not have that much of manganese, so this is kind of specific of tea leaves. It's known for a long time, and it is kind of part of essential analysis of tea. Manganese in tea leaves can be determined by many methods. One of them is very simple. We convert manganese into color permanganate after digestion and subsequent oxidation with potassium periodide. Any form of manganese, when treated with colorless potassium periodide, becoming deep purple permanganate. And it can be analyzed spectrophotometrically using any time of spectrophotometer, even the simplest. So the procedure will be as following. We take around half a gram of dry tea leaves and weigh them using analytical balances, so to the 4 significant digits. Next, we place them in a crucible and run digestion procedure. Usually it will be something like heating tea leaves to 500 Celsius in atmosphere of air when they will burn. Then increase temperature slightly, and what's left will be ashed, so all carbon will become CO2 and will be removed from our crucible. Same, of course, is true with water and nitrogen containing compounds. What's left will be metal oxides, including manganese oxide. All these oxides can be dissolved in a mixture of acid. Usually it will be sulfuric, some nitric acid, and maybe a little bit of phosphoric acid to mask iron-colored compounds. And the resulting solution will be transferred into 50 ml volumetric flask. The resulting solution, of course, will be warm. We add a little bit of sodium or potassium periodate, doesn't matter which one. What's important is IO4 minus ion, which oxidizes manganese. To do that, we need to heat the solution once again, so the purple color appears. And then we carefully dilute our solution to mark, so it will be exactly 50 mL. Next, we'll mix it well, take some part of it and put in 1 centimeter cuvette. We will be using only 1 cuvette, so its measurement, how precise this 1 centimeter is not essential, because it will be always 1 centimeter for all our samples and for standards we are using for calibration of our system. Next, of course, we need to calibrate. So we need to prepare standard solution of manganese and make permanganate by same procedure, and place it in a cuvette and make calibration curve running exactly the same instrument. Okay, we can use the simplest spectrophotometer, like this one, Spectronic, uh, and we are running absorbance measurements in interval from 0.2 to 0.8. Spectronic will give us, like many other spectrophotometers, 3 significant digits correctly. So we compare absorbances from our samples with absorbances at standard, and we calculate amount of manganese in our sample. I am not going over all these calculations. They are more or less trivial, and you can look at them yourself. So what about type B uncertainties? We are doing 3 types of measurements here only. First is vein of 0.5 gram. Uncertainty of analytical balances is 1 in 4 digits, 0.1 milligram, or 0.0001 gram. Tolerance of volumetric flask class A is 0.05 ml for 50 ml volume. Absorbance of 0.2, the worst case, has uncertainty of 0.01. Now, calculate relative uncertainties. Divide the uncertainty by amount we measure. Relative uncertainty of vein, as almost always, is very small. Relative uncertainty of our volumetric flask is visibly larger, 5 times larger, so it's obvious that we can skip the first one in our calculations. But uncertainty coming from spectrophotometric measurements are even larger. In case of 0.2 is 0.05. And keep in mind that we are measuring absorbances roughly twice. One when we are measuring our standard, and second time when we are measuring our sample. So this value need to be taken into account twice. So this is the largest type B uncertainty, and it will be bottleneck of our measurements if only measurements will cause the error. But our procedure is not very simple. You need to use oven, you need to treat your sample with high temperature, you need to add acids and never make a single mistake. Next, your tea leaves are not exactly uniform. They have different composition. One leaf is slightly different from another. So we have lots of sources of errors that are not coming from the measurements. Let's look at real example. What happens if we measure 4 samples of tea that were processed using this standard procedure I described? But of course, it needs to be described in more detail to run it. And the results are the following. For 4 different samples, we were getting these 4 numbers. They look very close to each other, can be processed using data analysis tool pack, and for 95% probability, I will have confidence interval of 0.0934 to 0.967. We can calculate relative uncertainty from there, and it will be much higher than our estimate. It's 0.17, and we compare to our uncertainty from type B, it's more than 3 times smaller number, which means all our type B uncertainties can be conveniently forgotten. the uncertainty coming from our parallel measurement is dominant, and it will describe the whole picture. Now, next, error of 0.17 here in two last digits can be rounded to 2, and our answer should be written in such a format: 0.095 plus minus 0.002%. Right format for our answer. Again, in our case, type B uncertainty did not play any visible role. Does it mean that we do not need them? Actually not. Let's look at next case. Here is our previous case with all calculations. Now, what will happen if only one our measurement, the first one, will be different? So it will be exactly the same as measurement number 3. Of course, it's very possible. You just have two measurements being identical accidentally. Now our results will give us very different statistics. Our numbers will be closer to each other, and confidence interval will be from 940 to 00953. Much more narrow. Now, of course, it will be included in this previous confidence interval, so there is no contradiction between these results. But relative uncertainty is much smaller and very close to 0.005, which was our type B tolerance. It is a good idea to increase our relative uncertainty from 0.07 statistical to 10. Why? Because we need to take into account that we are measuring absorbance twice, and it gives us uncertainty relative of 0.05. So this, and this will be 3 measurements, and our relative uncertainty from 3 sources of error will give us 10. So the answer will be not 947 plus minus 7 in last digits, but 0.947 plus minus 0010. We cannot round this 0. It will be wrong. We want to highlight that we have better precision. Still, the uncertainty is 30% larger than here. It's better estimate. It is more realistic result. And this is why we spend time estimating type B. We do not want to give our customer unrealistically good data. They may be looking better, but they are not. They are worse. Keep in mind that these two numbers, case 1 and case 2, do not contradict each other. Simply accidentally, case 1 was given larger uncertainty.